In question 5.35, we're being asked to apply Thevenin theorem to find the current over this 2K resistor. Well, before we do that, I'd like to have a quick recap on what is the method of using Thevenin or Norton theorem to find their equivalent circuit and simplify our analysis. So, simply put, there are three steps for finding Thevenin or Norton equivalent circuits. They are, firstly, find the open circuit voltage. Well, you need to firstly choose where do you want to separate the a part of the circuit with the rest of them, and find the voltage across those two separating terminals. Well, those part being separated is sometimes also being referred to as the load, the load of the circuit. Along with that, the second step for finding the equivalent circuit is to find the ISC. This is the short circuit current. Again, starting with those two separating points, you can conceptually adding a short circuit between them and find what will be the current through that short circuit. Well, after you find VOC and ISC, then the Thevenin equivalent resistance, RTH, equals their division. This looks like just applying the Ohm's law, but we actually specified how can you derive this from the textbook. Well, so that's the general step for finding either Thevenin or Norton equivalent circuits. There are two additional notes when applying this theorem. Firstly, if the circuit only contains independent sources, just as we've seen from the previous example, we can apply superposition to simplify our discussion. Specifically, in here, we can use superposition to find RTH directly. That is, setting the independent sources to 0, and the rest of the resistance will be the RTH you're looking for the equivalent circuit. The second note when applying the theorem is that there are some complexities when the circuit only contains dependent sources. So when the circuit only contains dependent sources, there's no energy being supplied. To find equivalent circuit for those type of question, you need to adding a probe source, that is artificially adding a voltage source or current source, and then compute, follow these three steps trying to find the equivalent resistance. Right? So after this quick recap, let's see how can we apply this method to solve this problem 5.35 here. Well, before these three steps, the first decision you need to make when trying to find the equivalent circuit is to make a choice on where to separate these two circuits. And actually, we mentioned during the separation, you need to make sure if there are dependent sources, the controlling variable and the dependent sources should be separated in the same part. But for this particular question, we don't have that complexity. And since we are looking for what will be the current across this 2K resistor, it will be convenient for us to separate it maybe just as these 2 points. Then, in this question, we're being asked to find the Thevenin equivalent circuit, and we know what we end up with will be having this Thevenin equivalent voltage source in theory with the Thevenin equivalent resistance, and then we're going to connect to this 2K resistor right across these two terminals. And one thing to note is that there are reference directions for the equivalent circuits. In fact, you should pay attention if you're drawing your equivalent circuit in this way, the top is the positive terminal and bottom is the negative terminal. And in here, since I0 is following our passive sign convention, so it's kind of convenient for us to just write it this way. Then our next step is trying to find what will be the VOC and what should be the RTH for the Thevenin equivalent circuit. Well, for this first question, let's try to apply these general rules this 3-step to solve this. We're going to start with trying to find VOC, the open circuit voltage in the circuit. Now let me redraw this circuit for this purpose. So what we have is so we're trying to find VOC right here. Notice the polarities here is corresponding to the polarity of my choice of the separation. Well, for this question, find VOC is actually not very hard. If you're looking at this, we can get VOC just by applying Kirchhoff voltage law on this loop. Here, I'm also kind of highlighting my reference directions here. The reason for this is when you're looking at this loop I draw here, we can easily compute all the voltage across each of the elements. So the voltage across this element, we're writing it here, will be well, notice here, the way I'm drawing this is if you're looking at this branch on top, we have one current source, and here is another current source. So the current from these two branches is known. Well, then it's easy for me to directly write what will be the voltage across my 2K resistor on top here. Similarly, in this branch, because the existence of the current source, I can easily compute voltage across my 1K resistor. So in the loop I highlighted in blue here, I can write my KVL as follows. I'll write it here. Well, if I'm examining this one here on my top resistor, well, my reference direction is entering the negative terminal. So this is actually negative resistance 2K multiplied by the sum of my current here. Maybe I'll write it out. So this is the voltage across my resistor on top. And then coming to this one here, if I'm assuming my reference direction is this one, so notice the current is entering my positive terminal following the passive sign convention. Then if I'm traversing this loop in this way, this again is a negative value. So I have negative 1K multiplied by the current here. And continue with my loop here. Here in the VOC, I have my positive VOC. The reason being entering the positive terminal, so following my passive sign convention. And lastly, when I'm traversing this last voltage source here, I end up with entering the negative terminal. So this is a negative volt here. And the algebraic sum for this is 0. So in this equation, I have, well, only one unknown variable here, VOC, so I can readily solve this. So in this way, I computed my open circuit voltage. Well, following my 3 steps here, my next step will be trying to find the short circuit current. And the way this one works is, well, I'm going to literally creating a short circuit in this branch and looking for how much current will go through there. So let me draw this circuit one more time. And also pay attention to my reference direction for this short circuit current. It's actually following the passive sign convention, so this is the current of interest here. Oh, so with this one, if I'm trying to find the current here, there are various ways to do this. One simple way for this probably will be using loop analysis. Well, in this case, I have two current sources, so I might want to take advantage of this. So maybe will be my first loop. I call this I1, and this one will be my second loop. I call this I2. There are some complexities when I'm trying to apply my loop analysis here. When there's a current source being shared by two mesh, well, I need to apply either the super mesh technique or the general loop technique. So here, maybe I'll just choose another loop. And I'm calling this general loop I3 here. Well, in this problem, I can quickly write, so for I1, because of the existence of this current source, and the I1's direction is the opposite direction of the current source, I1 is -2 milliamp. Similarly, I can write my I2 fairly easily. So I2 is this one. My reference direction is opposite to my current source. So my I2 is -4 milliamp. Well, for the last one, I need to write a Kirchhoff voltage law across my loop number 3 here. Well, the way I can write it is starting with my top resistor. I have 2K resistance multiplied by I3 plus I1. Well, because this resistor on top is shared by the two loops, I1 and I3 here. And continue to my next element here, I have this resistor, this 1K resistor here, and it's being shared by, again, I3, I1, but there's also I2. It's also shared by this I2 here. And notice the I2's reference direction is in the opposite direction as I1 and I3. So I have a minus I2 here. Well, continue here. I come to my voltage source. My reference direction is entering the negative terminal, so I have a -12. And the algebraic sum is 0. Putting these three equations together, I will be able to solve I3. So this is 3 equations with 1 unknown variable. But I'm not done here. So after I compute I3, what I'm really looking for is this ISC. So my ISC consists of 2 parts. The first part is the I3 that is going to the same direction as my short circuit current. And the other component is this I2 here, which is coming from the opposite direction. So I have minus I2. And this will be the ISC I'm looking for. Putting them together, well, apply my third step. In here, I can compute the corresponding RTH. Well, after I have find VOC and RTH, well, maybe I should write it here. So this RTH for this particular question equals VOC divided by ISC. Well, after that, I end up with a simple circuit, and I can easily solve my I0 here. So I0 will be, well, as you can see here, it will be VOC divided by RTH plus this 2K. Right? Well, this is the first way to solve this, applying the 3 steps and finding all the parameters in my equivalent circuit. There's a shortcut that we can take advantage if you're looking at this additional notes in my general problem-solving strategy here. That is, for a circuit like this, after I compute the VOC, the open circuit voltage, I can directly apply this additional nodes here. This circuit only contains independent sources, so that I can use source superposition to directly compute the 7 equivalent resistance. So we just saw the general approach when it's come to applying the 7-in or Norton equivalent circuits. This is following these 3 steps. Here's a shortcut, if you will, for a circuit that only contains independent sources. So for finding the 7 equivalent sources, for finding the 7 equivalent circuit for a circuit only contains independent sources, after step 1, finding the VOC, we can directly apply source superposition to find the 7 equivalent resistance. And this goes like this. So I just erased the part that we're computing ISC. We're not going to do this, but directly jump into how can we find RTH from the third step. By applying this idea of superposition, we're going to set all the independent sources to 0. And then our circuit becomes this. In here, notice what's happened after the superposition. Firstly, I'm setting my current sources to 0, and when current source being set to 0, they become open circuit. Then I set my voltage source to 0, and this voltage source become short circuit. Now, I can directly compute my 7 equivalent resistance by looking at the resistance across the 2 terminals that I'm making the separation. Specifically, I'm looking for what will be the resistance across these 2 terminals here. And for this circuit, it's easy to see that our RTH equals these 2 resistors in series. If you're looking at this, there are indeed 2 resistors in series. So with this observation, I can directly compute my 7 equivalent resistance is this 1K plus 2K, 3K ohm. Well, here, just as before, I computed my VOC. And with this shortcut, I got my RTH. I'm ready to solve what will be the current across this 2K resistor, which is this one of interest. So there you have it. You can always apply this general 3 steps to find your 7 equivalent circuit. Or in the special case where the circuit only contains independent sources, applies source superposition to directly find what will be the 7 equivalent resistance. And that will help you to quickly arrive on your 7 equivalent circuit. Well, that's all for this question.